Ah, Antonio, Antonio, Antonio. Rarely has there been one who is so confident, so condescending, and so certain he's right about everything he says, and yet so wrong in almost every way. Antonio has been racking up hours of YouTube time lately, with around 2 to 3 hours a day of his quote-unquote content dribbling across the airwaves. This video isn't about proving the shape of the Earth. Anyone with a scientific education above a 13-year-old's level can work out the answer to that one. No, this video is intended to show just how easily someone like Antonio can get something so relatively simple so very, very wrong. A week or so ago, he discussed an observation made by Jenna Friedel of the Toronto skyline from 30 miles away across Lake Ontario. Miles Davis had added an estimated auto level line showing where eye level should be from her location on the beach. Let's see what Antonio had to say about that.
Unfortunately for him, if that was level, the drop would be 0.04 degrees. Okay? 0.04 degrees would be the drop from this yellow line, which is supposedly Jenna Friedel, but in the distance, or a line projected from Jenna Friedel. You're Jenna Friedel right now looking out that way. The drop from that line to the horizon should be 0.04 degrees. It isn't though. We can see that even though we don't have the sun in the frame in order to establish how much a degree or a half degree is, but we can, anybody who's not too stupid can see that that's not 0.04. That's more than 0.04.
What's that, Antonio? You don't think that distance could possibly be 0.04 degrees?
The curvature says that there's a drop, okay, of 0.04 degrees. Well, here, between that yellow line and the horizon, is more than 0.04 degrees. Understand?
Yes, Antonio, I understand. I understand that you know literally nothing about calculating angular size. So I left a comment. Not under my account. Antonio blocked that a while ago. He doesn't like it when people prove him wrong. As I did a few months back, you can find that video on my channel, but he's since removed it. So I told him he seems to be mistaken about that eye level line, that I calculated it at about 0.042 degrees. He said then my calculations must be off. Place the sun's diameter in your calculations and see for yourself. So I went on to explain that we couldn't use the sun because it wasn't in the frame, but there are other items that we can use which are at a known size and distance, from which we can calculate their angular size. I left a couple more responses, finishing with a little wager, a bet. I bet Antonio £100 that I could clearly demonstrate that this was the case, that the angular distance was in fact around 0.04 degrees. When I hadn't had a reply, I left him another on the next day's video. I repeated my point and the challenge. In fact, I waived the £100. I said, look, how about if I can show you this, you publicly admit that you are wrong. Do you accept? And he did. Sure, knock yourself out, paste a link when you're done. Happy days, okay. So, here goes. Antonio, the answer to your question starts with this. Now I know it looks like a big scary equation, but don't worry, I'll walk you through it. This is the formula to calculate angular size, and just for you, Antonio, I'll walk you through how and why this formula works. If anybody watching already knows how this formula breaks down, feel free to go ahead and skip to the timestamp that's on the screen now. Okay, so for anyone still here, this is how this formula breaks down. First, we need to understand what angular size is. If this is your eye and you're looking at an object, then the light from that object is coming to your eye in a triangular pattern. We want to calculate this angle here. This is the angle between the light travelling from one side of the object to the other, whether it's the top and the bottom or the left and the right, it doesn't matter. If the object is closer, this angle will be larger. If the object is farther away, it'll be smaller. It's as simple as that. So how do we calculate the angle? Well, we can split this triangle of light into two parts. And this creates two right-angled triangles, both the same. If we work out one of these angles, then all we need to do is multiply it by 2 and we'll have the whole angle. We'll call this angle A. Now, as any high school kid will tell you, this is the adjacent side to that angle and this is the opposite side to that angle. And if we use tangent, we can find out that the tangent of angle A equals the opposite side over the adjacent side. Antonio, if you're not following this, then don't worry, you can go away, try this out yourself, draw a triangle, get a scientific calculator, I'll show you how in a minute, and you can work out the angle that it should be, measure it, and you can find out that it will be true. So to calculate the angle A, we just move tangent over to the other side, which makes it an inverse tangent, or arctan. So the angle A equals arctan, opposite over adjacent. How does this relate to the angular size formula? Well, if we're trying to work out this angle here, then that's twice angle A. We'll call this angle alpha. We'll call the distance to the object, which is the adjacent side, r, and we'll call the size of the object g, which was the opposite side before. This is 2 times the opposite side. When you simplify this equation down, you end up with angle alpha equals 2 times arctan g over 2r. So it's simply derived from basic high school trigonometry. Okay, so now do you understand the scary formula, Antonio? Good, let's move on. So we want to calculate the angular distance between the yellow line and the horizon. Well, first we need a benchmark object of a known size and distance so we can calculate its angular size and compare it to the distance we're looking for. Fortunately, we have a rather large building there, the CN Tower. The tower has a restaurant in the observation deck you can see, and that restaurant is 47.75 metres in diameter. We also know that the CN Tower is around 30 miles from the camera. So now we have these two measurements, we can go ahead and use our angular size formula. So the width of the restaurant G is 45.75 metres. The distance R is 48,280 metres, that's 30 miles. So to calculate the angular width of the restaurant, we just need to plug those numbers into our formula. So the calculation is 2 times the arctan of 45.75 divided by 2r, which is 96,560. And I'm going to show you this now with this calculator. Anybody can do this, Antonio, even you. So you'll see there you have your sine, cosine, tangent. If you press the second button, that turns them into a inverse sine, cosine and tangent with a little -1. So our calculation is 45.75 divided by 96560. That equals that. Now we take the inverse tangent, so click that, and now we multiply that by 2. And we get this. So, the angular width of that restaurant is 0.054 degrees. Now all we need to do is find out the ratio of the restaurant width to the height that we're looking for, and we'll have our answer. So measuring in Photoshop, the pixel width of the restaurant is 32 pixels wide. The pixel height of the yellow line above the horizon is 25 pixels. This gives us a ratio of 1.28 to 1. And if we divide the angular width of the restaurant, 0.054 degrees, by 1.28, we get 0.042 degrees. And there's our answer. So, Antonio, exactly what calculations did you do to determine that the drop could not possibly be 0.04 degrees, as predicted by Globe Maths? I've shown you clearly and conclusively using reference points in Jenna's own video that this seems to be 100% accurate. As I said, pal, I won't hold you to the 100 quid, but as agreed, I'll await your admittance that you were wrong. And if you're wrong about this, how many other things could you be wrong about? Oh, and in true Columbo style,
there's just one other thing, sir.
In your comment, you asked me to place the sun's diameter in the calculations and see for myself. Well, if the restaurant's angular width is 0.05 degrees, the Sun would be around 10 times this in diameter, something like this. Now I think this is where your misunderstanding comes from. You look at this and think the Sun could never appear this size relative to the buildings. But remember, this still was taken at almost full zoom of Jenner's P900. Zoomed out, and at the same scale, the Sun would look more like this. Does that seem about right to you? Right, well that's another one put to bed. If you liked watching a flat earther get wrecked, give this video a like. If you still think Antonio is the best thing since peanut M&Ms, then give it a thumbs down. Let's see which side wins. Thanks for watching.